Moving on to E2 reactions, we are going to look at the elimination concerted reaction. So let's just break down that name there, E2. E stands for elimination. The 2 stands for bimolecular, just like it did before in the SN2 reaction. So what we need to consider for this bimolecular reaction is the idea that both the electrophile and the base will be important for understanding the rate law. This will be a concerted one-step reaction. Now, when an alkyl halide is treated with a strong base, it can undergo these E2 reactions, also called beta elimination. The product is going to be an alkene. We make a new pi bond. Notice that the 2 sigma bonds are broken and 1 pi bond is formed. Let's just go over that curved arrow notation. The base will pick up a hydrogen. The hydrogen to carbon's bond, electrons will roll down to make the new pi bond and will kick out the leaving group. So there is a proton transfer and a loss of a leaving group happening at the same time. Now, a strong base will react in a concerted mechanism. So that base needs to have a negative charge. It needs to have some sort of really reactive electrons, right? There's only one case that we'll see later where a strong base doesn't have a negative charge, and that's a nitrogen lone pair. We'll present that at the end of our discussion of E2. So with E2, it's a concerted reaction where the base removes that beta proton, the hydrogen attached to the beta carbon. That causes the loss of the leaving group and the formation of the carbon-carbon double bond. It's concerted, right? So the rate law is dependent on both the base and the electrophile or the alkyl halide. So just as the SN2, that 2 standing for bimolecular, the E2 also stands for bimolecular. One thing that I want to present here is this idea of how this reaction takes place. Similar to how we had the backside attack in our SN2 reaction, we have a very specific orientation for this E2 reaction. And I want to draw a perspective diagram here. I'll put in the hydrogens so that we can kind of start to identify those tetrahedrals on both the alpha, the carbon with the leaving group, and the beta, the carbon with the hydrogen right next door, right? And what's really important is that when this base comes in to do that first initial proton transfer, think about the trajectory of where that base is coming in and where the leaving group needs to be. And notice how I drew these. They are on opposite sides of each other. Just like in the backside attack, where the nucleophile had to come into the electrophile on the opposite side, so too does the base need to be deprotonating the beta carbon on the opposite side of the leaving group. So as those electrons roll down to become the pi bond in between alpha and beta, the leaving group is getting kicked out in a backside attack motion. This is what we call anti-peri-planar. Let's deconstruct that word for a second. Opposite sides, anti to each other. H is on the top, leaving group on the bottom. Periplanar, meaning they're within the same plane. Notice how they're on that same straight line plane of my 2D piece of paper here. They need to be within that same plane directly on top of each other. And that is the only way that we can get that carbon-carbon double bond to form successfully. We protonate the base, so we get a conjugate acid, and we get our leaving group. Let's just label alpha and beta one more time so that we can see that double bond exists between alpha and beta. So a very specific orientation here. Why we don't need to consider a nucleophile by definition, why we switch to the base idea, is considering hydroxide here. Hydroxide functions as both a nucleophile and as a base. But one thing that's really important is that tertiary alkyl halides can actually undergo this E2 reaction. We can have primary, secondary, or tertiary alkyl halides for our electrophile. And the main reason for that is because notice the big difference here in understanding substitution versus elimination of a tertiary center. Hydroxide cannot get to that alpha carbon in a substitution reaction, but the beta carbon is detached from that, right? So looking at that reaction, that extra bit of room allows hydroxide on a tertiary alkyl halide to function as a base. So even though we can't do the direct substitution, because the alkyl halide is too sterically hindered and the nucleophile cannot penetrate and get in to attack that alpha carbon because of that steric hindrance, that nucleophile can actually function as a base instead, and a beta proton can be abstracted. So it's really important that when we're thinking about these reactions, that we are going to start to see their similarities and their big differences to our SN2 reactions, right? So they're very, very similar, but they are different in what is required for each one. Now, when we form an alkene, this is something that now we need to start thinking about. We are changing in this product. We are changing the stereochemistry. We are changing the hybridization of our alpha and beta carbons. And so one thing to remember is that isomerization idea. So we could create alkenes that are cis or trans. Let's just remember trans, which is E, and cis, which is Z. We will be making these. Again, when we identify these alkenes as products, we would be able to start to identify which one is more favored. So when we think about these, if we were to make both products, and we'll practice this a lot together, but if in a specific reaction we were to make isomers, stereo isomers, we have to consider steric hindrance on this. The trans is always more stable than the cis. And that is due to the fact of steric hindrance, right? The trans keeps those groups on opposite sides, whereas the cis puts the biggest groups or the higher priority groups together, and there's this steric hindrance that's bumping into each other on the same side idea. There's combustion data that goes with that, but this is just one of those ideas that when we start seeing a specific reaction, so let's do something like this guy. And we'll just focus today with this one on the E2 reaction. What we want to be able to identify are a couple of things. Here's my alpha. I have beta, and I'm going to say beta 1 and beta 2 because they are two different sides, right? And this is a reactive base. Has a negative charge. If we think about the conjugate acid of water, pKa of 15.7, that is stable, right? So the main one that I want to think about here, the main beta, is beta 2. Right now there's a specific alignment. The anti-periplanar hydrogen that I see is the one that's opposite. And so what we get from that is the trans. Notice how the two R groups are on opposite sides. I'll highlight them here. So they end up on opposite sides in this concerted mechanism. However, what if we were to rotate around the alpha and beta 2 bond? What if I were to rotate so that one hydrogen went to the back that wasn't in the back to begin with? That other hydrogen, namely this guy, he could be rotated to the back to be anti-periplanar. And then when my hydroxide comes in to attack, I get a different stereochemistry. Notice how these carbon groups now starting to look on the same side, and that they are trans versus cis. So there's the ability to make both cis and trans if you have two hydrogens on your beta carbon. And if that internal double bond is formed, you can make cis and trans. Trans will always be the major product versus the cis will always be the minor product due to stability. Some other stability that we can see is that alkyl groups stabilize the carbon-carbon pi bond. And so the more R groups you have, the more stable you are. Notice mono substituted has 1 R group, di substituted is 2. From that, what we can see is the cis is lower in energy than the trans. And then tri-substituted with 3 R groups and tetra-substituted with 4. So when there's more than one option for your beta, let's talk about that, right? When there is more than one option for your beta carbon, beta 1, methyl is different from ethyl, right? This is also beta 1, but it's identical. Those two methyl groups on that alpha carbon are identical. So we only have to consider one at the moment. I'm going to consider the one on the left instead of the one up at the top. Now, it is very common to have more than one beta carbon. And so thinking about a strong base, again, ethoxide, think about that is a sodium to oxygen ionic bond. Sodium has a +1 charge, spectator ion. You can just kind of remove it. Ethyl is attached to the oxygen that would have a minus charge. I like to separate those and then say, ignore the sodium +1. That spectator ion is there. Yes, it balances out our minus charge and it will keep balancing out our negative charges, but it's a spectator. It's not important for this one. Now, there is going to be what we call regioselectivity, right? We talked about stability of the alkene just a few seconds ago. Now we're going to talk about, okay, when we have all of these different alkenes, namely what happens when we pull off a hydrogen on beta 1, right? We get the alkene that we see on the right. What happens if we were to pull off a hydrogen on beta 2? We get the molecule on the left in the products. Well, how can we predict these values? The more substituted product will be called the Zaitsev product. The less substituted product is called the Hofmann product. The size of your base will determine which one is higher in concentration. So for this example, because the size of ethoxide is relatively small, The Zaitsev product is in higher quantity. It is the major product. I really like this chart from our textbook because it's looking at regioselectivity with these values, and numeric values for me always helped. And we can kind of see this dividing line right here of when is too big. So Zaitsev products are favored when you have small bases. Ethoxide, methoxide, or hydroxide. Once you get past those three, then your base gets very large, and steric hindrance does play a factor on which product, the more substituted or the less substituted alkene, is favorable. So we can actually control the product favored by controlling the size of the base. If we want a more substituted alkene, we'll choose a smaller base. If we want a less substituted alkene, we'll go with the Hofmann base, the larger base. And so notice that these are very large molecules, and all of a sudden we start favoring our Hofmann product. The Hofmann becomes major. A couple other bases that you can see here. Nitrogens, very, very common one, diisopropylamine, or triethylamine. Those are also Hofmann bases. They would favor the less substituted alkene to be produced. The last thing that we would want to talk about is just another example of stereochemistry, stereoselectivity. Stereoselectivity is the idea that anti-periplanar is needed for the E2 reaction to come about, right? And that we, even though we have that anti-periplanar, we will always favor trans over cis, right? That's selectivity. We're selecting which product we want. The reason for that selection is because trans is more stable than cis. There is less steric hindrance in that product. We also have another word we're going to introduce here, stereospecificity. That again is that anti-periplanar nature. There is a specific orientation that will result in the possibility of only one product. So I want to draw this molecule for us first. pH is an abbreviation for a phenyl group or a benzene ring. So you can think just very, very large group there. I'm going to draw on very specific orientations here. And let's just use sodium methoxide. I like to keep the sodium on there to remind us of our ionic bonds. Now what we see on this molecule, what I've laid out for us is the alpha and beta position. I want to go through that molecules, this curved arrow mechanism one more time, and we'll get plenty of practice together in class. I'm going to separate that ionic bond, and notice how I drew the anti-periplanar nature. Now this molecule is stereospecific for our product. Why? Because there is one beta hydrogen. There's only one beta on this whole molecule that would have a hydrogen. Notice there is a beta also back here, but why I'm not presenting that is because there is no hydrogen on that beta. The only beta that has a hydrogen is the one shown. So let's do that curved arrow. Base goes to pick up the proton transfer. Electrons immediately roll down opposite side of the leaving group. Now, how do we draw that carbon-carbon double bond with my beta and alpha? Well, let's look at and highlight some things in my original structure. Wedged phenyl group, wedged hydrogen. Those are on the same side. And again, dashed methyl, dashed tert-butyl, those are on the same side. So analyzing that anti-periplanar nature, it is locking our alkyl halide in a specific conformation. That conformation is the anti-periplanar. So there's going to be a specific alkene that we can make for each hydrogen that we can deprotonate. So for this one, we will only make the E isomer. The Z is not observed because there is no hydrogen that would be anti-periplanar to the halogen leaving group in the Z conformation. As we're diving into this, the book goes through a lot of ideas with Newman projections. Again, what we want to do is practice drawing our hydrogen, the beta hydrogen, and the alpha carbon leaving group, usually a bromine or a chlorine or an iodine, anti-periplanar to each other so that we can truly understand what alkene stereochemistry we are going to result in.